Okay, welcome to Chapter 3, Optimizing with GHG. In the last chapter, we reviewed how the market dispatches resources, how to set prices, how to verify that the marginal cost of congestion is what it is when there's a transmission constraint. And in this chapter, we're going to layer GHG on top of that. There are three main concepts or aspects of GHG design that allow us to optimize market dispatch with GHG. First is separable GHG bid adders. The separable GHG bid adders allow the market to dispatch at least cost consistent with separate jurisdictional preferences. Because they're separable, we're able to consider the market where unregulated resources don't have a GHG cost, and then consider the market where unregulated resources do have a GHG cost, or as if they were in the regulated area. And this will tell us what resources outside of a GHG regulated jurisdiction are economic to serve the regulated area, while simultaneously helps us prevent the cost of GHG regulation from impacting the cost paid by load in the rest of the market. The second key concept here is the GHG export allocation. This tells the market how many megawatts of capacity to attribute to a GHG regulated area. So, in other words, if California, in addition to its internal capacity, needs an additional 100 megawatts of capacity from outside of California in order to serve load, then the GHG export allocation would be 100 megawatts. I know it sounds like it should be a GHG import allocation, and it's sort of a misnomer. Don't blame me for that. But what we're really doing is exporting capacity from the unregulated area to the regulated area. The third key aspect here is the marginal cost of GHG. And this is a different concept from the marginal cost of compliance paid by resources. You'll recall that in the previous chapter, I made a distinction between a resource's bid price and a resource's marginal cost in order to create a convention where it's clear that when we say the marginal cost, what we mean is the shadow price of the power balance constraint. So here it's sort of the same thing, where the marginal cost of GHG is not referring to a resource's compliance cost, but it's referring to the value we get when we relax the GHG export allocation by 1 megawatt. And that tells us what the cost of serving the GHG regulation area is compared to the non-GHG regulation area. This value is produced by the market optimization, and it ensures the efficiency of price formation and helps us settle efficient market outcomes. Now, I realize this is a very dense slide, and I just said a lot of new words, but I'm going to spend the next 139 slides or so illustrating these concepts. So don't worry if it hasn't sunk in yet, we're going to get there. First, let's dig a little bit more into what these bid adders are. I've put a screenshot of the model that we're going to work with on the left. It looks similar to the example we looked at in the previous chapter where we had two balancing areas. But instead of balancing area 1 and 2, we have a GHG and a non-GHG area. Resources can submit a two-part bid adder for each GHG area. And in this presentation, we only have one GHG area that's on the left of the model. So that unregulated resources, those are on the right, they will only submit bid adders for the GHG regulated area that we have on the screen. In the real world, we might actually have more than one GHG regulated area where multiple states have carbon pricing policies. But for the purpose of this presentation, we're just going to stick with one GHG area, and regulated resources submit that bid adders for that area to signal how the market should optimize dispatch. So the first part of this two-part adder is a megawatt quantity, and that says what the megawatt quantity a resource is willing to offer to the GHG area. This is a very important concept because GHG participation is entirely voluntary for resources that are outside of a regulated state. resources have to opt in to tell the market that they're willing to fulfill the administrative reporting obligation and the monetary compliance obligation that comes with serving a GHG regulated area. The opt-in nature also allows resources to hold back some capacity if that capacity is being used to fulfill regulations or contractual obligations elsewhere. So in short, the megawatt quantity portion of the bid is an opt-in, and it tells the market what capacity a resource is willing to opt for consideration to transfer to the GHG area. The dollar per megawatt quantity is the second portion of this bid, and it reflects the cost associated with the resource's expected compliance obligation in the GHG area. So, for example, Unit 2 does not expect to have to pay any compliance obligations. It will have to fulfill administrative reporting obligations, but it's a clean resource, so its expected compliance cost is zero. By contrast, let's look at Unit 3, which is an emitting resource. So for every megawatt that's attributed from Unit 3 to the GHG area, this resource expects to have to pay $6 per megawatt hour in compliance costs to cover the cost of its emissions. And this actually raises the marginal cost of the resource, or it raises the full bid price of the resource only if it's attributed to the GHG area. If we consider this resource for dispatch to the non-GHG area, it only costs $30 per megawatt hour. So sometimes we refer to this as the marginal cost of emissions, but as I said in the previous slide, we're going to stick to the convention that we set up in Chapter 2, and I'll refer to this as the resource's GHG bid price, or its compliance costs. You'll note that Unit 1 just says $35 at the top, and there's no megawatt quantity or dollar per megawatt GHG bid. Unit 1 is located in the GHG area, and a resource does not need a GHG bid adder for its own jurisdiction. These resources don't opt in because they're in a state that requires compliance from them no matter what. We attribute resources we don't attribute resources that are already located in the GHG area because LMPs in the GHG area already reflect energy and compliance. And I'll show you how this works in practice in Chapter 4. I've summarized all of this in the chart at the bottom. 1 is already regulated, does not get attributed, and therefore does not submit a GHG bid adder. Units 2 and 3 in this example submit bid adders that tell the market that they're willing to offer their full capacity to the GHG regulated area. The GHG bid on Unit 2 is 0, so the GHG area views the bid price of this resource as $35 per megawatt hour. The bid adder on Unit 3 is 6, so the GHG area views this resource as a $36 per megawatt hour resource. So let's dig into this example a bit. Again, this is switched up a little bit from the example in Unit 2, where instead of BA1 and BA2, we have a GHG and a non-GHG area. I've also relabeled load. So we have load in the GHG area, and we need 200 megawatts to meet load. We also have load in the non-GHG area, labeled LN, and we need to meet 50 megawatts of load there. So let's find dispatch and prices. When the market optimizes the system, it's going to try and satisfy the preferences for load in both areas at the same time. We're going to take it step by step though, because I'm a human, not a machine. So we need some steps to understand this. Let's start with the non-GHG area. I've removed the GHG costs, and you'll note that that only impacts Unit 3. It does not impact the cost of Unit 1, which might have a GHG cost, but it's already accounted for in its energy bid. But even if we use Unit 1 to meet load in the non-GHG area, it would still have a compliance cost if it's an emitting resource because it's in a regulated area. So that stays the same. And the prices reflected on your screen right now are the bid prices of resources that are relevant when we consider dispatch to the non-regulated area. So we need to meet 50 megawatts of load, and the least cost resource available to us, according to non-GHG area preferences, is Unit 3, which costs $30 per megawatt hour. So we'll take 50 megawatts from Unit 3. Now, how do we set prices? If we increase load in the non-GHG area by 1 megawatt, we would take the next megawatt of capacity from Unit 3. So the marginal cost of serving load in the non-GHG area is $30 per megawatt hour. And this is efficient. It's efficient because we only need 50 megawatts of capacity from Unit 3, and this is sending the correct price signal that this is what minimizes the cost of serving load in the non-GHG area. Now let's take a look at the GHG area. How do we dispatch resources and set prices? Well, compared to the non-GHG area, now Unit 3 is no longer economic. It costs $36 per megawatt hour to dispatch and to meet load in the GHG area. So we'll have to take capacity from either Units 1 or 2. And we're indifferent between these two. You'll notice that we know that Unit 2 is a clean resource, or at least it's telling us that it has $0 in compliance obligations. But we don't know what the compliance cost of Unit 1 is. We don't know what its emissions are. But it also doesn't matter because we're optimizing to find the least cost solution. So we want to account for both energy and compliance. The energy plus compliance cost of Unit 1 is $35 per megawatt hour. The energy plus compliance cost of Unit 2 is $35 per megawatt hour. So we're indifferent between paying $35 per megawatt hour and $35 per megawatt hour. You'll also notice that we don't have a transfer constraint, and that means that it's unclear what the export allocation is. And this is unusual. Usually there's enough complexity in the market, we have binding constraints all over the place, and there's lots of different generation with lots of different bid prices, and we're able to figure out what the export allocation is. In this case, I noted that it's unusual, and it's unusual because not only do we not know what the export allocation is, but it also doesn't matter. We're going to get the same clearing price for what the marginal cost of GHG is, no matter what the transfer is from the non-GHG to the GHG area. If we need to meet the next increment of load in the GHG area, so we need to meet the 201st megawatt of load, we know that it's either going to come from Unit 1 or Unit 2. And because they cost the same, the LMP in the GHG area is going to be $35. This is the price signal that Unit 1 responds to. It's the marginal cost of meeting the next increment of load in the GHG area, and it's the price that load in the GHG area will pay for power. And when we did this for the non-GHG area, we found that the LMP was $30 per megawatt hour. And that's going to give us a price difference. Even though we don't have a transmission constraint here, there's a difference in LMPs. And that's because of a difference in GHG preferences. So the marginal cost of GHG is the cost to the system of a marginal export to the GHG area. Usually we would prove this by relaxing the GHG export allocation, and that still holds true here. Whether we're taking 200 megawatts from Unit 1 or 200 megawatts from Unit 2, no matter what that is, when we relax it by a megawatt, we still see the same change in cost to the system. So I'll show you what that looks like on the next slide. I've picked a random GHG export allocation, and we're going to say that we take 200 megawatts from Unit 2. If 200 megawatts from Unit 2 are used to serve load in the GHG area, that means we have a 200 megawatt GHG export allocation because we're exporting 200 megawatts from the we're exporting 200 megawatts from the non-GHG to the GHG area. What does it look like to relax that constraint? Now, we don't want to change the power balance constraint. We did that in Chapter 2 when we wanted to find the LMPs. We're not looking for the LMPs. We're not trying to figure out what the marginal change in supply costs looks like because of a change in load. What we want to do is figure out what the cost of the system is because we're serving a GHG instead of a non-GHG or an unregulated area. So when we relax the GHG export allocation, what we're doing is shifting 1 megawatt from the GHG area to 1 megawatt in the non-GHG area. And this is a simplification, but it's the easiest way to think about it. And when we do that, we're able to dispatch down 1 megawatt of Unit 2, or Unit 1, if you've chosen that to dispatch in this situation. Either way, we're able to dispatch down 1 megawatt of the more expensive resources and dispatch up 1 megawatt of Unit 3. And since we're shifting a megawatt from a regulated area to the non-regulated area, Unit 3 only costs the system $30 per megawatt hour. So relaxing the GHG export allocation in this case saves system costs $5. And that's going to be our marginal cost of GHG. The GHG export allocation carries the cost of regulation, which can either be compliance or energy costs in excess of what the non-GHG area is willing to pay. It represents the difference in preferences between the GHG and non-GHG areas' idea of what least cost dispatch should look like. And it helps us make sure that the GHG area is paying for what they prefer and what they're responsible for. We find the marginal cost of GHG by relaxing the export allocation by 1 megawatt. If we substitute 1 megawatt of the export allocation for 1 megawatt of capacity needed to meet the non-GHG area, in the previous example that meant that we could use this $30 resource instead of the $35 resource, that reduced the cost of the system by $5. And that tells us that for an incremental increase in serving the GHG area cost the non-GHG area $5. One caveat before we move forward. In this presentation and in the market today, the marginal cost of GHG shows up as a negative component of the LMP in the non-GHG area. So in this presentation, I'll say the marginal cost of GHG is -5. In the extended day ahead market, the marginal cost of GHG will be reflected as a positive component in the GHG area. And I'll be able to show you in Chapter 4 what this looks like in practice, but the key takeaway should really be this. The sign change is a difference in convention that makes it easier for us to calculate and settle costs in the market, but it does not change the solution found in these examples. It does not change the LMPs, and it will not have an impact on market outcomes. It's just something that I wanted to highlight for you, given that this is an Evergreen training and it will be on YouTube, hopefully, past when the extended day ahead market goes live. So it's important to note. So to summarize what we've talked about so far, in the example we just went through, we did not know what the GHG export allocation is, but we also didn't need to. And this is not typical. The marginal cost of GHG is actually a function of the GHG export allocation and the relative cost of resources eligible for attribution in the non-GHG area. In the example we just went through, any GHG export allocation, whether it was 0 because we were taking all of the capacity we needed from Unit 1, or 200 because we were taking all of the capacity we needed from Unit 2, in either case, we would get the same marginal cost of GHG. And we call this a degenerate solution, where we get to a solution even though there were lots of different pathways toward it. In life and in electricity market optimization, we usually have to deal with a lot more constraints and a lot more information. So in Chapter 4, I'm going to be using a transmission constraint in order to help us more clearly calculate the export allocation and arrive at the marginal cost of GHG. A transmission constraint is the clearest way to illustrate a GHG export allocation, but we can also have a transfer between the non-GHG area and the GHG area anytime there's a price difference in the available generation between the two areas. If you're an economist, or you are like me and you think that you're an economist, you might say that the GHG export allocation has something to do with the marginal elasticity of supply in the GHG area relative to the non-GHG area. And I will show you an example of that in the next slide. So I really like this example for a couple of reasons. The first thing to note is that I've changed the megawatt quantity or the megawatt capacity of these resources, and I've changed their bids a little bit. Unit 1 is a 300 megawatt resource just like before, and it costs $50 per megawatt hour. Unit 2 is a 200 megawatt resource. Its energy bid is $31 per megawatt hour, but its energy plus GHG cost is $35 per megawatt hour. Unit 3 is now a bigger resource. We have 300 megawatts of Unit 3, and it costs $30 per megawatt hour if it serves either the GHG or non-GHG area. And you'll also note that there's no transmission constraint, but we do have an export allocation because of the price difference between the available generation in the GHG and the non-GHG area. The least cost resource for both areas, for load in both areas, is going to be Unit 3 at $30 per megawatt hour. And this brings me to the second thing that I really like about this example, which is even though we do have an export allocation, we're going to be exporting 200 megawatts of Unit 3 from the non-GHG to the GHG area. There's no difference in preferences for what least cost dispatch should look like here. Both the GHG and the non-GHG area agree that Unit 3 is the cheapest resource. So because there's no difference in preferences, there's no marginal cost of GHG. The LMP in both areas is the same. Load in the GHG area will pay $30 per megawatt hour for 200 megawatts of capacity, and load in the non-GHG area will pay $30 per megawatt hour for 50 megawatts of capacity. But because Unit 3 gets this export allocation, Unit 3 will still have to fulfill the reporting obligations that come with the 200 megawatt export allocation it receives. Because it has a zero GHG bid adder, it likely doesn't have to pay any compliance instruments to cover those emissions. This is a different example where we have the same resources as before, and load is the same, but now we run into a transfer constraint. We can only dispatch up 50 megawatts to meet load, and 100 megawatts can be transferred out in the non-GHG area. That means we can only dispatch up 150 megawatts total from Unit 3. So 50 megawatts of Unit 3 will be used to serve load in the non-GHG area. 100 megawatts of Unit 3 will be used as the GHG export allocation. But then we have to take 100 megawatts of Unit 1 in order to serve the rest of the load in the GHG area. And this creates a price difference. This is the same resource as before, and we're still meeting load at least cost in a way that both the GHG and the non-GHG area agree with. So there's no divergence in GHG preferences here, but we get price separation, and that is due to congestion. And you can prove this to yourself the same way we did in Chapter 2, where we increased the transfer constraint from 100 to 101 megawatts. And if we do that, we can substitute 1 megawatt of Unit 1 for 1 megawatt of Unit 3, and that saves a total system cost of $20. So now we're going to put all of these concepts together. When GHG preferences diverge and the GHG area's preferences impose a cost on the non-GHG area, this price separation is accounted for by the marginal cost of GHG. When we add a transmission constraint in the mix, we also get a marginal cost of congestion. So in the example on your screen, you see the LMP in the GHG area is $50 per megawatt hour. The LMP in the non-GHG area is $30. That difference of $20 can be accounted for by $15 in congestion and $5 in GHG. And I'm actually not going to dissect this example at the moment because it is the first example in Chapter 4. So before we get there, I'm going to take a pause, reflect on some key takeaways, and if after seeing that last slide you feel like you need to do some reviewing, now is the time to go back. But if you're mentally prepared to dive into Chapter 4, we'll just wrap up here and say that the difference in LMPs between the two areas account for some combination of GHG and congestion. When there's no difference in LMPs, there might still be a transfer between those two areas. And in that case, load in each area will only pay for what load in that area is responsible for. That part of the problem is part of the settlement of the solution, and we'll break that down in Chapter 4.